Okay, as you can see, this first warm-up problem, first thing you notice is this negative infinity right here. Oh no, what can I do? Well, as we learned from the previous section, you can take 1 over the power to the least value, which is on the bottom. But because it's negative infinity, I need to multiply it by 1 over negative x, and then on the top I'm going to multiply by 1 over the square root of negative x quantity squared. When I do that, then that ends up equaling, oops, let me make this, actually, this equals the limit as x approaches negative infinity of the square root of 1 minus 9 over x squared over negative 4 minus 3 over x. When I plug in negative infinity to this, then basically this doesn't matter. This becomes a square root of 1 over, this doesn't matter, negative 4, which is negative 1/4.
For the second warm-up problem, we see that it equals a number, which is 1. When you plug in the number, it's 1 minus 5 plus 4 all over 1 minus 1. This gives you 0 over 0, which means it is indeterminate. So then you have to go ahead and you have to factor it. So you have the limit as x approaches 1 of x minus 4 times x minus 1 all over x minus 1. And wow, these cancel out. Cancel, goodbye. So then you have limit x approaches 1 of x minus 4. When you plug in the 1, this will give you an answer of negative 3.
Okay, in the third warm-up problem, we see that this is the limit as x approaches 1. No way, you can actually plug this one in. So, you can just say 3 times 1 squared minus 5 times 1 plus 1 over 1 minus 3. That would be 3 minus 5 plus 1 over 1 minus 3, which is equal to negative 1 over negative 2, which is equal to 1/2. There we go.
So for our last warm-up problem, we have another limit. But you can't just assume that it is indeterminate, even though it is in the indeterminate section, so we gotta plug it in. So we have the square root of 3 minus the square root of 3 all over 3 minus 3. That unfortunately equals 0. So let's erase that work. And we have to look at this problem and we say, what can we do? How about a conjugate? So we're gonna multiply this by the square root of x plus the square root of 3 all over square root of x plus square root of 3. This will give us x minus 3 all over x minus 3 times the square root x plus square root of 3. And this will give us the limit x approaches 3 of, well, since these cancel out in case you were wondering, 1 over square root of 3 plus square root of 3, which gives us an answer of 1 over 2 square root 3, or, can't forget the or, square root of 3 over 6. So whichever one is for your liking, you may take.
For the next 4 problems, we're going to find any discontinuities that there might be in these functions. The first one is a trigonometric function, and basically you need to ask yourself, is there any place that I can't plug in an x value? The answer is no, you can plug in any x value that your little heart desires, so therefore there are no discontinuities. And also, if we look at this graph on a calculator, that's what it looks like. You can see that the graph is continuous. Alright, for this one, you gotta remember that the denominator cannot equal 0. So therefore, we are going to set this equation equal to 0. X minus 2 equals 0. When we solve that, we find that there is a discontinuity at any point when x is 2. The next one is a little tricky. So, tangent of x, you might think, what the heck? But let's think about tangent of x a different way. This is the same thing as saying f of x is equal to the sine of x over the cosine of x. Now remember, we can never have the denominator equaling 0. So therefore, we have to find a place where cosine of x is equal to 0. That's at pi over 2, 3 pi over 2, places like that. So, when x is equal to 0 is at places when it is pi over 2 times n, where n is an element of real functions or real numbers that are odd. Alright, for this last problem, we gotta remember that the denominator cannot equal 0. Therefore, to find when x can't equal 0, we're going to set the denominator equal to 0. Square root of 3 minus 2 times the cosine of x is equal to 0. When you solve this, cosine of x is equal to root 3 over 2. Let's think about this in terms of the, the unit circle, that's what it's called. When you draw these out, where the cosine of x equals 0 is when x is equal to pi over 6 and when x is equal to 11 pi over 6. But then you have to keep in account that sometimes these can circle a ton of times, so you have to add 2 pi n to each of these. And these are your answers.
And theorem 2.6.1, wait, hold on, it's in red, different color. Mark this on your page, guys. Don't forget this. If c is any number in the natural domain of the stated trigonometric function, then the limit as x approaches c of sine of x equals sine of c. Also, the limit of cosine of x as x approaches c equals cosine of c. The limit as x approaches c of tangent x equals tangent c. The limit as x approaches c of cosecant x equals cosecant c. The limit as secant x as x approaches c equals secant c. The limit as x approaches c of cotangent x equals cotangent c. Do you see a little pattern going on? But in case you don't understand what that means, just remember to plug C in. In case you don't understand what that theorem meant, we're just going to jump right into a problem. So the first example problem is the limit as x approaches infinity of sine of 1 over x. From the last theorem, we figured out that we could take sine to the outside. So the sine of the limit as x approaches infinity of 1 over x, this ends up being the sine of 0 because 1 over a huge number is eventually just going to end up to be too small for us to comprehend, so it turns into 0. So the sine of 0 equals 0 because of the unit circle. Where is sine equal to 0? Equal to 0 there. And this is how